Okay, here is a basic related rates example using similar triangles, and similar triangles are a pretty simple concept, but uh, if you read this particular problem, you'll notice that it does not say anywhere that we're dealing with similar triangles, so we have to sort of extract that for ourselves. And I've drawn a picture here. So we have this man here, and he's walking towards a lamppost, and of course the lamp is on, it's nighttime, there's a shadow casted, so that's what's in green here to indicate that's where his shadow is. And when you draw this picture, you can see that the smaller triangle has the same angles as the larger triangle, the big triangle, so they are similar triangles. So we can use some proportions to look at the different sides. So I've got my generic picture set up. I have to put in some variables here for the things that are changing with time. So the man is walking towards the lamppost at this rate. That's a specific number that's at a particular moment in time, so I'm not going to use that. The light is 22 feet above the ground. I've already got that labeled. At what rate is the length of his shadow changing? So I need something in this picture to represent the length of his shadow. So his shadow's here. I'll call that length x, and of course that changes as he gets closer to the lamppost. And then at what rate is the length of his shadow changing when he is this far from the base of the lamppost? Of course that number is changing too, so let's call his distance from the base of the lamppost y. And the length of his shadow is x, okay? So now we need a relationship from this picture relating x and y, some sort of equation. Since these are similar triangles, I know that the ratio of, let's say, of the smaller triangle, the green side to the vertical side, that ratio, x over 5.75, that ratio is equal to the bottom side of the big triangle to the vertical side of the big triangle. So the bottom side is x plus y. So that equals x plus y over 22. So all I did is set up a ratio for my similar triangles, and now I have a relationship that I could try to use. So I'm going to differentiate both sides of this with respect to t, but before I do that, let's make our life a little easier by rewriting the equation like this. Let's sort of pull the constants away. X divided by 5.75 is the same thing as this fraction times x. And over here, we have 1/22 times x plus y. Now when I take my derivatives, it's much easier to see what's going to happen because those constants can just be pulled away. Again, I'm differentiating with respect to time because I want to know how fast the length of his shadow is changing. In other words, how many feet per second is the time unit we see here. Also notice I forgot to mention I converted 5 feet 9 inches to feet specifically, which is 5.75 feet. Okay, now let's differentiate. So when I differentiate the left side with respect to t, the x goes away when I do the derivative of this product, but now I have to multiply by the derivative of x with respect to t, so by dx dt. And similarly on the right side, you get 1/22 times the derivative of this stuff. The derivative of x is dx dt, and the derivative of y is dy dt. Now notice how I still have this in parentheses because the 1/22 applies to both of those. Now I need to plug things in that I know and solve for what I don't know. In this question, I'm asked at what rate is the length of his shadow changing, so I'm looking for dx dt. I'm given that he's 10 feet from the base of the lamppost, so if I draw my specific picture, I could do a better job, but this is just for quickness. I know that this is 10, so in other words, y is 10 at my specific moment. Okay, this is still 22, this is still 5.75. However, notice over here I don't need to plug in any y's. I need dx dt and dy dt. Dx dt is my unknown, which means I need a value for dy dt. So if I go back to the problem, a man is walking toward a lamppost at a rate of 5 feet per second. That is, specifically, that's how fast he's moving towards a lamppost. So that's the rate of change of y. But since it's getting smaller, since y is getting smaller, that's actually going to be -5 instead of +5. So I'll plug that in, and I will solve that equation for dx dt. So I have 1 over 5.75 dx dt. I will distribute my 1/22 here. So I have 1/22 dx dt. 1/22 times -5 is -5/22. Sort of separate these here. And now I need to solve for dx dt. So I'm going to subtract this term to the left, and on the right I will leave my -5/22. Now I need to get dx dt out of this so I can solve for it, so I'll factor it out. And of course I have this 1 over 5.75 minus 1 over 22 equals -5 over 22. And I'm going to create some more room here now that we understand what's happening. And finally, all I have to do to solve for dx dt is to divide by the stuff in the parentheses here. So I have -5/22 divided by 1 over 5.75 minus 1 over 22, and so dx dt is approximately, and if I use my calculator properly, I got -1.77 approximately feet, because x, remember, was the length of the shadow, feet per time second. So his shadow at this moment in time, the length of his shadow is decreasing at 1.77 feet per second, and that makes sense. The closer the man gets to the lamppost, the shorter his shadow is going to be. So the length of the shadow is decreasing as he gets closer to the lamppost.